Hello, this is Teach Nichols, and this lecture is on thermodynamic closed systems and entropy. The essential question is, how do we define a thermodynamic system, and how and why does energy move around inside a closed system? So let's start off by defining how we could even make a closed system for thermal energy. It's kind of tricky, right? The only truly closed system is the entire universe, but if we want to make kind of a localized closed-ish system, what would it look like? Well, if we don't want thermal energy, remember variable U, to get in or out of the system, that means we need to prevent this system from exchanging thermal energy with anything else in the universe. In order to do this, we would have to have a perfectly sealed, rigid, airtight box. In this box, we can't let light go in or out. We can't let heat go in or out. We'll define that a little bit later. We can't let energy go in or out, which means we can't have any outside forces pushing on the stuff inside the box or allowing the box to push on them. And we obviously can't let any mass kind of escape or enter through the walls. In the next couple videos, we will examine what it looks like to be an open system for thermal energy, which is obviously a more common situation in the world because it's pretty hard to have a closed system for energy. So let's imagine that we have two systems, two relatively closed systems at different temperatures, and we're going to combine them into a single big closed system. When those two systems come into contact, since we're closing them together, we are allowing energy to move from one to the other until they reach a new stable equilibrium temperature somewhere in between. This should be sort of intuitive, right? If you take a glass full of ice cream and pour hot coffee on it, you know the temperature it's going to end up at is somewhere between the temperature of the hot coffee and the temperature of the ice cream. Um, the energy spontaneously, which means on its own, will move from the hotter system to the cooler system via one of three processes. Those processes are called radiation, convection, and conduction. The process of radiation is a really interesting one, and actually we're going to spend a lot more time on it in the spring when we talk more about light. But the idea is that photons, which are tiny pieces of light, leave a system and actually take some of the total energy and temperature of the system with them. Turns out every object in the entire universe is kind of doing this all the time. We are all radiating, we're all spitting out light all the time spontaneously. But the hotter the objects, the greater the amount of radiation is coming from them. This spontaneous radiation from every object in the universe is known as blackbody radiation. Blackbody radiation is what is generating the light we see from stars. So they're spontaneously spitting out little pieces of light, and the hotter the stars are, the more light basically spits out of them. But it turns out humans are black bodies as well. We're much lower temperature black bodies, but we're actually spitting out radiation all the time. It happens to be a color of light that our eyes don't detect. It's in the infrared spectrum, but humans are also radiating away our energy all the time. The second sort of passive process by which systems transfer energy to each other is known as convection. Convection occurs when we have two systems containing liquids or gases and we combine them. Because liquids and gases kind of have fuzzy boundaries or loose boundaries with the materials on the edges, the warmer and colder particles in those systems actually can migrate from one system to the other and mix with each other. Sometimes this is called bulk movement. The particles, the hot particles actually move from one place to another. You should be familiar with this from lots of processes in your life. For example, heating up water on the stove, right? The hot particles on the bottom of the pot actually move up to the top. They get warmer, and that causes them to expand their boundaries a little bit, expand the bonds between them and the nearby atoms, which makes them less dense, which increases the buoyant force on those particles, and they actually go to the top. So hot water created at the bottom of the pot rises, and then something else has to replace it, which is the colder water that was near the top. And so the entire pot of water gets very hot very quickly because the particles are actually moving. The hot ones are moving around, and so are the cold ones. Heating systems in rooms are designed the same way, right? We'll have our warm air source near the floor because as it heats air, that air rises, and then new colder air will fall and be replaced as it passes through the heat source. We also see this in our own Earth, convection currents inside the Earth's mantle. The rock is heated up near the outer core. It rises, it pushes out volcanoes and ridges and that kind of stuff, and then it cools down and comes back down to the outer core where it gets formed and does it again. The third process is called conduction. And conduction happens when you have two objects that have solid boundaries. So we can't actually move the particles through the boundary or from one to the other. Instead, those particles exchange energy or pass energy from one system to the other via collisions that are happening in the molecules that are at the boundary. And those collisions transfer energy until eventually they move all the excess energy from one of the systems into the other, and then we're at equilibrium. So for example, if this is the boundary between two materials, we've got a hot material on the left, which means all of the particles are moving quickly, and a colder material on the right, where the particles are moving slower. So the ones on the left have high energy, and when they hit the ones on the right, they actually transfer that high energy to the colder ones, which then move off faster and heat up, right? So if you take two objects, two solid objects that are at different temperatures, you will notice that the hot one becomes cooler as it transfers the energies through these collisions, and then the cold object is going to become hotter as well. There is a very special name for energy moving in or out of a system by the process of conduction, and that is called heat. So this is a little problematic because you've all used the word heat a lot in your lives to mean lots of different things, but in physics, heat is very specifically energy moving into or out of a system by conduction only. The variable that we are going to use for heat is a capital Q, and heat is an energy, which means we can measure it in joules, just like all of the other kinds of energies. Heat can be a positive value or a negative value. Because heat itself always implies transfer of energy, positive Q means gaining energy by heat, and a negative Q is going to mean the system is losing energy from heat. If you had a closed system, right, the overall delta Q in that system is 0. We are going to move the heat around, but not create it or destroy it. If you take two systems and combine them into a single bigger closed system, you will find one of those systems has a negative delta Q, the other one has a positive delta Q, until the overall system's at equilibrium. But those two values should cancel each other. There's a very funny equation on the equation sheet that I would say basically does one thing. It lets you calculate the rate of heat transfer through a surface by conduction. So it tells you how much Q every second is going to be moving through a surface. That should be a lowercase t, but the font is only letting me use uppercase. So Q divided by delta T. So the rate of heat transfer depends on a handful of things. Number one, it depends on how different the temperature between the systems are. If I put a room temperature glass of water down in the room, there's not going to be a lot of heat moving in or out of that water. But if I put a really, really hot glass of tea down in a very, very cold room, then the difference in temperature between the two systems is large. Heat moves very quickly when there is a big difference in temperature, and that's a linear relationship. The second variable is the surface area in contact. So since this heat is moving through collisions at the surface, the more surface you provide, the faster the heat is able to move from one spot to the other. This should make a little bit of intuitive sense to you, right? Obviously, like touching something cold with your whole hand or hot with your whole hand is a much worse idea than with a fingertip, because touching it with your whole hand allows a lot more heat to move in and out of your hand, depending on whether the object is hot or cold. So the third variable is called the thermal conductivity. This is a material constant every material would have. And it basically is tied to the way that the material can store energy. Some materials can only store energy with movement, and those materials tend to have a pretty high value of K. Other materials can store energy other ways, like rotating or vibrating. And if you have more ways to store energy, then that means it's going to be harder to move heat through you because you can store up that energy in other formats. The last variable is the thickness of the material, and we actually use the letter L to represent thickness because T was taken by temperature and time in this equation. Um, and so obviously, if you have to move the heat through a thick material, it's going to move slower than if the material was thin. So on that teapot, that would be like the thickness of the bottom of the teapot as it moves from the heating element into the system of the water. So here's the equation on your equation sheet. Q over delta T equals K, which is the thermal conductivity, times the area of contact between the materials, times delta T, which is the temperature difference, divided by L. So I guess hopefully you're asking yourself, why does the energy bother moving anyway? And it's a little complicated. It's kind of a mystery of the universe. But in any case, we've named this mystery entropy. Entropy, you may have heard of before, sometimes is defined colloquially as chaos, but in general, a thermodynamic system is considered to have a lot of order or low entropy if the hot and cold particles are separated, it's organized. And a system is considered disordered, which is high entropy, if all of the particles are mixed together, we've got some hots and some colds. So there is an important law, second law of thermodynamics. I realize we haven't learned the first yet, but we're starting with this one, that says that the disorder of any system is always spontaneously increasing. This is kind of the opposite of a law of conservation, right? It's saying this is for sure not conserved in the universe. In fact, it's always increasing, always over time. In other words, everything will become more chaotic. It never becomes more organized. It always becomes more chaotic. That isn't to say that it's not possible to reverse the disorder of a system or make something more organized in the world, but there is a cost. If I'm going to put the energy into creating order, I'm also going to create a lot of disorder in that process by heating things up or moving other things around. So no matter how hard you try to make something ordered, you're going to create more disorder in our universe over time. There's a bunch of good comics and t-shirts that have to do with the nature of entropy because it's kind of a mysterious thing. Okay, so I'm going to go ahead and wrap up this lecture. I know this got a bunch of little tidbits of information, and we're going to do a lot more work with these things as the weeks go on. But in any case, please do take a second and wrap up by thinking about your essential question. How are we defining thermodynamic systems, and how, and maybe a little bit of why, does that energy move around inside the closed systems? Thanks for watching.